Assalamu alaikum. Welcome back to our fine-tuning of the universe lecture series. We are now on lecture 6, and we are going to, inshallah, finish up today the initial conditions of the Big Bang. As you've seen with us, this is one of the best examples of fine-tuning, how precise the Big Bang had to be in so many different respects. It was not just some haphazard explosion, but it had to fulfill very, very, very precise initial conditions to allow the universe to be hospitable to life. And we are going to finish up this discussion of initial conditions today, inshallah, and then in later lectures move on to other examples of fine-tuning that involve things like the fundamental constants of nature. So let me attempt to begin this video with a demonstration. Again, just trying to make things a little more exciting here. So here is an ordinary cup of water. And here I'm going to put in some red liquid. And you see the red liquid flowing into the water. And then I'm going to stir liquid. And now the water is pink. And so, well, let me just leave it at that. We will discuss this demonstration in a little bit, but hopefully I have piqued your interest. What could that possibly have to do with the Big Bang? Well, the last condition we want to talk about regarding the Big Bang is the need for a low entropy Big Bang. This is actually one of the most stringent conditions. And to understand this, we have to talk a little bit about the concept of entropy. It is one of the most important concepts in physics and one of really the most difficult to define. But entropy features in what is known as the second law of thermodynamics. And one way to think about entropy is that low entropy is needed to do useful work. And after useful work is done, then entropy rises. And the second law of thermodynamics basically says that in any closed system, entropy always rises. So one example of that is that if you have a hot system and a cold system, like a hot tub of water connected to a cold tub of water, heat will flow from the hot to the cold spontaneously until the temperature equalizes. And this entails a rise in entropy. And this flow of the heat from the hot area to the cold area is something that can be used to do useful work, and in fact is one of the basic principles behind a combustion engine. The second law of thermodynamics is so important that Arthur Eddington, who was a famous physicist in the early 20th century, he basically provided the first experimental proof of Einstein's general theory of relativity. And he said something very interesting that I want to share with you about the second law of thermodynamics. He said that if someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, Maxwell's equations, by the way, are the famous equations of electromagnetism, then so much the worse for Maxwell's equations. If your pet theory is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There's nothing for it but to collapse in deepest humiliation. So basically, the second law of thermodynamics, that entropy always increases in a closed system, is considered absolutely fundamental to our modern understanding of the universe, to theories of physics. So another way to understand entropy is that things become more disordered with time, and that this always happens. So that basically, if you take a box that is a vacuum and put some molecules in it, over time, the molecules will then spread out in the box. Here is a more ordered arrangement. Here's a more disordered arrangement. And that disorder increases with time. And we will always know that this arrangement came before this arrangement. If you toss a bunch of bricks off a truck, they're not going to fall in an orderly stack. They're going to fall in a more disordered pattern. So that disorder increases with time. You know this very well, for example, from things like dropping an egg on the floor. The egg will break, and that has to do with motions of molecules that make up the egg. Now, there's absolutely nothing in the laws of physics that would forbid those molecules to reverse their motions and for the egg to put itself back together again. But we know that that never happens, even though there is nothing in Newton's laws, for example, that would forbid each molecule to take a reverse course and for the egg to come back together. But we know from Humpty Dumpty that all of the king's horses and all of the king's men can't put Humpty together again, right? Eggs do not unbreak. And now here is the demonstration I tried to demonstrate to you. Here is food coloring being added to water. And when you stir the water, the food coloring mixes in, and the water will become a homogeneous color, like this clear water is now pink. Now, if you keep stirring, there is again absolutely nothing in the laws of motion that would forbid the individual molecules from collecting again into discrete droplets of water. So there is nothing to forbid in the laws of physics that if I keep stirring my cup, that the water molecules and the molecules of dye would rearrange themselves into discrete droplets like this in a cup of clear water. But you know very well that I can take my cup and I can literally keep stirring until the universe ends, and the red droplets will not recollect inside a cup of clear water, even though there is nothing in the laws of molecular motion to forbid this. Why is that? It is because of the second law of thermodynamics. The second law of thermodynamics, which is a statistical law, forbids that from happening. So we always know that the colored water came later than this picture of individual droplets. So the second law of thermodynamics has been used to explain the arrow of time. The broken egg is always before the unbroken egg. The discrete droplets of color in the water are always before the homogeneous colored water when they mix in and diffuse into the water. So the reason time flows from backward to forward and not from forward to backward is because of the second law of thermodynamics. It gives us a way to order events. And when the food color mixes into the water, we have increased the entropy of the system. This is a more orderly arrangement, but the colored water that is now homogeneously colored, like this cup, this is now a higher entropy system than when I first put the droplets in. So that's yet another way to think about entropy, is increasing disorder, and that the increase in disorder underlies the arrow of time. And we can see this, for example, in that a hot cup of coffee always cools, although there is nothing in physics to forbid a cold cup of coffee from getting hotter, except the second law of thermodynamics. Ice spontaneously melts. We do not see, after it has melted, if the temperature in the room is greater than the melting point of ice, we will never see water molecules recollect into ice cubes. Even though, once again, the only thing that forbids this is the second law of thermodynamics. Water will flow spontaneously from a higher place to a lower place, but it will not rise up from a lower place to a higher place. All of these are examples of the second law of thermodynamics and of increasing entropy. The melted ice is higher entropy than the ice cubes. The cup of coffee equilibrated to room temperature is a higher entropy system than a hot cup of coffee in a colder room. This arrangement is a lower entropy system than when the water flows down and fills this lower cup and so forth. And again, it is impossible to give a full explanation in just a few minutes, but I'm just trying to give you a flavor of what entropy is. And all of this boils down to that the second law of thermodynamics is basically a law that says that usable energy, energy to do useful work, decreases with time. So if I have a whole bunch of usable energy before, then now I have some usable energy and some unusable energy. And with time, free energy, usable energy to do useful work decreases, and unusable energy increases. That is what the second law of thermodynamics is saying. And so once again, low entropy is needed to do useful work, which then raises entropy. Now, you know that all of life on Earth is dependent on us getting energy from the sun. But probably a lot of us think that we simply absorb the sun's light, and that gives us energy. What a lot of people don't realize is that the Earth gives the energy back. We can't just keep absorbing energy from the sun. Otherwise, the Earth would heat up and heat up and heat up and boil and evaporate. So we give off just as much energy as we absorb every single day. However, the energy that we absorb from the sun is in the form of low entropy photons that can be used to do useful work. And then the Earth radiates back photons that are, let me rephrase that, I'm sorry. What we absorb from the sun are basically high frequency, high energy, low entropy photons. I hope that is what I have said. What we give back are low frequency, low energy, high entropy photons. So we absorb photons that are capable of doing useful work, and we give back photons that are not capable of doing useful work, even though the total amount of energy is the same. We absorb energy from the sun and radiate energy back, but the kind of energy that is absorbed and the kind of energy that is given off are different. This is low entropy energy, this is high entropy energy, and the difference in entropy is what powers life on Earth. That is, for example, the energy that goes into photosynthesis underlying all energy on Earth. So we absorb a few high energy, low entropy photons, and we give off many low energy photons that cannot be used to do useful work. So let's just read this together from this website. So let's look at this process from the overall energy entropy balance of our planet. Like each of us, Earth is in an approximate state of energy equilibrium. Our planet receives as much energy as it loses. Although the in-out energy almost balances, or really it does balance, the in-out entropy doesn't. The heat the Earth radiates into space has a much higher, about 20 times higher entropy than the incoming visible light energy we receive from the sun. The low entropy light coming in is useful energy, while the high entropy heat leaving is essentially useless. The sun then is the source of Earth's useful low entropy energy. I will let you read the rest of this on your own, but the idea is that the low entropy of the sun is what allows life on Earth to happen. And the question then is, where does the sun's low entropy come from? How did we get a low entropy sun that can give energy that allows the useful work of life like photosynthesis to happen? It originated in the gravitational collapse of the diffuse cloud of gas from which it formed 5 billion years ago. And that low entropy stuff originated in the Big Bang, the unfathomable but highly ordered event that birthed the universe. Your body's organization comes from the Big Bang. In the 14 billion years since, the entropy of the universe has steadily increased. So here's our bottom line. The reason the universe can sustain life is that the Big Bang was extremely ordered and extremely low entropy. And it is that low entropy of the Big Bang which has allowed things like stars to form and those stars to have low entropy photons that can power life. Now, the Big Bang did not need to begin in a low entropy condition. The Big Bang could have been a disordered, chaotic Big Bang, as we talked about in the last video. We had different reasons for discussing ordered versus disordered Big Bang, but for today's video, the take-home point is that the Big Bang needed to be in an extremely ordered, low entropy state for the universe to be capable of supporting any form of life. How low entropy did it need to be? This is probably the single most amazing number in all of physics. So Roger Penrose, who, if you follow science news, has just recently won the Nobel Prize in Physics for his work on black holes and Einstein's general theory of relativity. He has calculated that of all of the possible configurations of the Big Bang, the low entropy, highly ordered state said that the accuracy of the creator's aim, if you were just picking universes at random, would have had to be 1 part in 10 to the 10 to the 123. And here's the reference for that. This number is unfathomably large. It is beyond our ability to even remotely comprehend. If the accuracy had to be 1 part in 10 to the 10 to the 1, instead of 10 to the 10 to the 123, 10 to the 10 to the 1, well, what is 10 to the 1? 10 to the first power is 10. So that would be 1 followed by 10 to the 10 zeros only, which is accurate to 1 part in 10 billion. If it were 10 to the 10 to the 2, well, 10 raised to the power 2 is 100. So it would have to be accurate to 1 part in 1 followed by 100 zeros. That's a number I don't even know what to call, except that it's called a Google. But in terms of billions and trillions, obviously it's a very trillion. That's how large. 1 in 10 to the 10 to the 3 would be accurate to 1 part in 1 followed by 1,000 zeros. So imagine if the power here is now 123, 1 in 10 to the 10 to the 123. Well, let's read this paragraph together. Again, here's its citation. The low entropy condition of the early universe is extreme in both respects. The universe is a very big system, and it was once in a very low entropy state. The odds of that happening by chance are staggeringly small. Roger Penrose, a mathematical physicist at Oxford University, and again, recent Nobel laureate in physics, estimates the probability to be roughly 1 in 10 to the 10 to the 123. That number is so small that if it were written out in ordinary decimal form, the decimal would be followed by more zeros than there are particles in the universe. Actually, many, many trillions, trillions, trillions more zeros than there are particles in the universe. There are probably about 10 to the 80 particles only in the universe. Shouldn't say only, but you can get the idea of how staggeringly big this number is. It is even smaller than the ratio of the volume of a proton to the entire volume of the visible universe. Imagine filling the whole universe with lottery tickets the size of protons and choosing one ticket at random. Your chance of winning that lottery is much higher than the probability of the universe beginning in a state with such low entropy. Hugh Price, a philosopher of science at Cambridge, has called the low entropy condition of the early universe, quote, the most underrated discovery in the history of physics. And there is probably no better example of fine-tuning of the universe than the universe beginning in the low entropy state, which it did. And again, Roger Penrose is saying that the accuracy of the creator's aim would have had to be 1 part in 10 to the 10 to the 123. That is a more precise initial condition than we can, by any stretch, begin to fathom. And for us as people of faith, it is a resounding testament that this universe capable of supporting life did not occur by chance. And so I hope that this has piqued your interest. I hope, inshallah, that you will continue to tune in, because as I said at the beginning of this series, there are many doors to faith. And when I have talked to Muslim young people, they have told me that this notion of fine-tuning of the universe has been something very significant to them in an age where people are trying to paint out that science does not support faith, that sophisticated, intelligent, scientifically advanced people do not have the need for the notion of God, astaghfirullah. We see that the fine-tuning arguments make a very resounding rebuttal of that, and that the science of the last 50 years has taught us that it is essentially impossible for this universe to be a product of chance. So take care, Assalamu alaikum, and God bless.